Hi, so today we're going to start section 5.1. The content of this is about sequences, which I'm displaying the textbook here. You get a bit of terminology to figure out, and then we'll proceed to work with it. So what is a sequence? Basically, I actually don't quite agree with the definition that's in EP. I would say a sequence is a function whose domain is the natural numbers. And I would use the term finite sequence to talk about the situation she's given here. So she says either the domain is all the integers between two given integers, so it goes from A to B, or as she's written it, from M to N there. Or it's a domain its domain is something that starts at a particular spot and goes forever. Well, so if you go from M to N, I would call that a finite sequence, just to be explicit about what your meaning is. But it's a bit of a quibble. I think that it's the definition here is fine. So what we mean is a list of numbers. They can be real numbers, complex numbers, even integers. The way we usually distinguish the elements that are in a list is to put a little subscript on them. So we see A sub M, and they talk about that. You read it as A sub K if you mean the kth one. Each of those numbers that's in the sequence is called a term. So that's the same phrase they use for the elements of a polynomial. You talk about the terms in a polynomial. So these are the terms in a sequence, the parts that make up the whole. The subscript is called an index, right? And we can talk about the initial term and the final term if we're talking about a finite sequence. I would say that if you're talking about an infinite sequence, you might as well make the initial index be 0, right? So you can start from A0 and go on forever. That may mean sort of a deal where you have to renumber things, but it's not hard to renumber things. So, but you can always define things as you want. And in this book, they're just defining it to start at M and go forever. Okay, so let's do some examples of that stuff. Let's see. First, I'm going to need to switch my view of the video. So hang with me one second. Okay, so that's a way we can do a display of a graphing calculator. And I think folks will have used the graphing calculator to make sequences in the past already. So what have I got in here? Let's set y equal, well, that'll be fine. Y equals 1 over x. If you set a formula in your y equals thing, and rather than hitting the graph button, you hit second and that button, you'll get the table. See the yellow table there. So effectively this, although it's not starting where it normally does, let's start it at 1. The y column here contains the elements or the terms of the sequence we're talking about. So there's the first term, there's the second term, there's the third. As decimals, you might not recognize this as being 1 over x or 1 over n. But if you think about what these look like as fractions, you probably would. That's 1, that's 1/2, that's 1/3. We recognize 1/4 and 1/5. Do you see 1/6? Probably not that often. 1/7, that's actually something you might recognize because of the decimal approximation for pi. Pi is really 3.14159, but 22/7 is 3.14286. Yeah. 1/8 you recognize probably, 0.125 is an eighth. And 1/9 is ones repeating forever. And 1/10 is easy. And then they start getting weirder. So, but the point is usually you look at the first few terms of a sequence and you want to try to guess the formula. All right, so we can do that with a graphing calculator, but well, let me give you an example with the graphing calculator. So I'm going to secretly put in a different formula. Let's see. I better start it where it's supposed to start. So I've made up a formula, and there's the corresponding terms. At 0 we get 0, at 1 we get -1, then at 2 we get 2, but at 3 we get -3. At 4 we get 4, and at 5 it's -5. Are you getting the pattern? Really, playing with sequences is mostly about recognizing patterns. So one way people could say this is, if the number is even, just say it. And if the number is odd, say it's negative. You can express a function, because that's what a sequence is, in that form. F of x is equal to, it's got two options. If it'll be x, or it'll be the negative of x. And we do this if x is even. Oops. And then we do the other thing if x is odd. But it's also possible, because I just put it into my graphing calculator and I got an answer, or I got the thing to plot the sequence we're talking about, to print out the sequence we're talking about. It's also possible to give a single answer. And that's a bit of trickery that I think you should get to know. You can put -1 to a power into your formula, and then whenever your x is an even number, -1 to an even power will have an even number of minus signs in it, right? So that'll be positive. Have I done the right thing? Yeah. So if I put -1 to the x, I'll make all my even terms be positive and all my odd terms be negative. And then I want the actual value to just be x itself. So multiply this thing times x. Now if I wanted to switch it so that the odd ones were positive and the even ones were negative, I could do a similar thing. It would just need to change the power there on the, instead of x, use x plus 1. Right? Let me prove to you that I'm not lying. Here's the formula I put in, -1 to the x times x. See? Let me just start fresh. Let's put in -1 raised to the, got to use parentheses around the exponent or that won't work. X plus 1, right? Because of PEMDAS. And let's times that by something different so that it looks more interesting. How about x squared? And then we'll look at that in the table. Now here, well, the 0th entry is just 0 the way I've worked things out, but notice now it's the negative terms. I said that wrong. The even terms that are negative. And what are they the negatives of? They're squares. You spot that 16 is 4 squared and 25 is 5 squared, etc. So the only difference is the minus signs that are in there. Okay. Let's also talk about this in computer algebra, because the graphing calculator, frankly, is kind of a primitive tool. So I'm going to start up a Sage worksheet and I'll be back. I'm not going to be back because I'll edit the video and you'll just see me. Alright, so while I was away, I know you can't tell I was away, but I was. I started up a CoCalc session, and I want to lead you through some of the processes around using the system here. There's basically file manipulation. If you have existing files, they'll appear under the Files tab. So this is the file I was working in the last time I showed you some stuff about graphs. If you select one of those things, it's got a checkbox next to it, you can do a variety of things to it. For instance, you can rename it. Where is it? Is it? Change the name. I didn't recognize it with the just the graphic thing, but you know, maybe I didn't need to have this time date stamp as part of its name. I could just call it graphs. Fine. Okay, but the other thing that you're going to need to do from this screen is be able to create a new thing. Obvious, I think. Click new. Again, by default, the name it's going to give you is the date followed by a timestamp. Let's see, yeah, it's 11:25 in the morning while I'm working here on March 31st. I'm going to add something that's human readable, or more human readable to that, so that I'll recognize its name. Now, there's a lot of different things that you can create. LaTeX is a document preparation system, Sage itself, Jupyter Notebooks. You can just do Markdown. There's even an X11 desktop. That means you can run terminal commands. But anyway, we're going to use this one, a Sage worksheet. So, I'm going to write a for loop. And if you're familiar with Python, this works similarly. If you write the command structure, the things that happen inside the loop or inside the if or whatever other command you're doing are just shown by indentation. And it's a smart editor, so it automatically indented 4 spaces for me. Let's just print the value of I here. And that's all. That's what the loop I'm interested in should do. It's thinking an inordinately long time for such a simple action. Alright, so that printed the values 0 and 10. Not quite what I wanted, is it? Oh yeah. I believe I put the dot operator in there if I mean the entire range. Oops. Fingers skipped onto the wrong key. There you go. So that's a way to make a sequence that starts in one place and ends in another. If I wanted to start at 17 and end at, I don't know, 31, there you go. That's the sequence. So this is A sub 17, A sub 18. They're just the numbers themselves. If I wanted a more interesting sequence here, I'd have to provide, a formula for it. So suppose I wanted to make it be I to the second power divided by I plus 1. Now, I'm not sure I would recognize these numbers. Maybe I'd say, thinking way back, 289, isn't that a square that I learned when I was doing the times tables past 12? Except, yeah, maybe not. So, with these larger numbers, you might not spot the pattern that you're looking at a square over the number 1 greater than the square root of that thing. This would be, that would be an interesting one to guess at. If you we're looking at sort of smaller numbers, like maybe 0 to 10, then you might say, okay, I can see the pattern. Right? The numerators are squares and the denominators are, well, they're not the numbers that we're squaring, but they're one bigger than the numbers we're squaring. And so you might guess at that formula. So the direction I've just shown you, coming up with a formula and then seeing what the values are, that's really easy. The hard thing is going to be the reverse, right? Looking at a sequence and trying to figure out what formulas they use to get those numbers. And it's like many things, it's something that the more you play with it, the better you get at it. But I'm not sure if it's really an essential skill for being good computer scientists. There is another thing that is a very common syntax we do with in programming, which is this. You set a variable, you initialize it to some value in front of the loop, and then inside the loop, you add to it. So there's a shortcut command. You can say x plus equals, and then maybe let's just have it add I to itself each time. So we'll start at 0. The first time through the loop, the loop variable I will be at 0. So first this does nothing. And then it begins to do things because I is non-zero after that. Let's have it print out what x is if we run this loop. Okay, so like I said, the first time through the loop, you're adding 0, and so x is still 0. That's what we're seeing right there. The second time, the I value is 1, so x is 0, but we add 1 to it, and yep, 1. Now x is holding 1, right? So the third time through the loop, the loop variable is 2, and we're adding 1 and 2 and getting 3. These are numbers that actually are very familiar to people, I think. They're called triangular numbers. And I've got to start up the video. Sorry, I'll get this little webcam thing set up so that I can draw things. So if you have a triangular array of dots, so the sort of trivial triangular array has just got a single dot in it, then you can have 3 dots, 6 dots, right? If you know about bowling, you've got this pattern. And how many pins are there in the game of bowling? 10. Right? So these triangles have the corresponding number of dots that I'm talking about. 1, 3, 6, 10. Did we see those in the? Sorry, get rid of that screen. Did we see those in the pattern here? 1, 3, 6, 10. 15. Pool players, people who play billiards, will recognize that number. I don't know of any games that do 21 or 28, etc. But there they are. There is another place where you will see the triangular numbers, and I think it's worth pointing out. Oops, just got to bring the screen back up. The triangular numbers occur in Pascal's triangle, which I believe many of you will be familiar with. This is a triangle that's used it's used in a variety of settings. It's great for helping with probability questions. I think its original purpose was to figure out how many subsets are in a set. But what is the deal with this triangular pattern I'm drawing for you? Each number in it is the sum of the two things above it. One to the left, one to the right, add them up, and you get like 3 and 3 is 6. 1 and 3 gives us this 4. I can fill in the next row then. Oh, why is it 1 on the outside? Well, it's sort of like there's a 0 out here that's kind of not really there, but anything outside the triangle is zeros, so 0 and 1 gets me 1. And that means you always begin and end the rows with 1s, and everything in the middle is gotten by adding the stuff above it. Right. So that kind of doesn't really belong there. That's Pascal's triangle. Do you see where the triangular numbers are sitting inside of this triangle? It's kind of cool. They're all in one of the diagonals. Right? If I were to write the next row down, 5 and 10 would give me a 15 right there. And that is indeed the next triangular numbers. So, yeah, triangular numbers are a pretty cool sequence. Can we come up with a formula for them? I just used the Sage thing to create them by adding I ones each time we bumped up the form. But I would like a t sub n, a formula in terms of n here that would give me these numbers. So the first one is 1, the second one is 3, the third one is 6, etc. And there's sort of a clever way of doing that. This is kind of cool because it goes back to ancient Greece. I'm going to get another sheet to draw on. In the Greek world, they talked about a certain category of numbers. They actually had a lot of numbers that were treated this way. They called them figurate. that is, numbers that had to do with some sort of figure. And that is the smallest rectangular number. Actually, I think the technical word for it was oblong. They call them oblong numbers. This is rectangular arrays that are 1 unit longer than they are tall. Right? So like the way we often write 6 dots, I think that's what you see on the face of a dice, right? That's an oblong number too. So the first oblong number is 2, the next one is 6. What would the next guy be? It's 3 tall and 4 wide. Oh, so it's 3 by 4, right? So that oblong number is 12. And the thing that's cool, that's related to the triangular numbers, is you can cut these things in half along diagonals, and you get 2 copies of the triangles. Right? It's actually really easy to think about a formula for the oblong numbers. O sub n is, this is the one that would be, let's see, n tall and n plus 1 wide, so it's n times n plus 1, right? And then t sub n, the triangular numbers, are easy from there because they're half of what the oblong numbers are. So t sub n is n times n plus 1 over 2. I'm a little concerned I might be off by 1 with this calculation. That is, let's see, let's check. When n is 1, what number should I get in the triangular numbers? It should be 1. 1 times 2 over 2. Okay, cool. It does work. So that's a fun example of a pair of sequences that are closely related. One's actually really easy to figure out. The other's maybe a little stretch. So one last thing we need to talk about with the sequences is how do you denote mathematically this thing that we just did here on the Sage worksheet, adding up the terms of a sequence. There's a thing called sigma notation. Whoops, hiding the screen. Sorry, sigma notation. And sigma is the Greek letter for S. So it looks kind of like a letter E. In fact, a lot of people think that's a Greek E, but it's really an S. Sigma S, it's actually supposed to be shorthand for sum. So how do you do sigma notation? Well, you put some kind of formula, often, or you can just talk about the term of a sequence in there. And then you put a low limit and a high limit, just like you did in the Sage worksheet. Remember how we went from 0 to 10 here? Well, you just need to control that index variable. So you start it somewhere. Let's go 0 to 10. And you take it up to a high value somewhere. So this notation, n equals 0 to 10, sigma in summing a sub n, means add up all the terms of the sequence a sub n from the 0th one all the way to the 10th one. That is, this is equal to a0 plus a1 plus, that's going to get boring, so let's just write dot 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 plus a10. If I were interested in telling you about the triangular numbers, t sub n would be equal to a sum where the sums, I'm going to use I for the sum variable, starts at 0 and goes to n, and what we'll add is I. So think about what that means for different n's. Here I've got a sum that, the way I'm writing this, the n is a variable that's changing as we go through it. So that's cool because what we're creating is a definition for a sequence using some other sequence, the summation or the partial sums of a sequence. So T0 is the sum that goes from 0 to 0 of I. So that means it's just a 0. t sub 1 is a sum that starts at 0 and then goes to 1. The thing that I wrote down there were 0 and 1 themselves, right? So that's the values of the index. 0. So that's 1, right? T sub 2 would be 0 plus 1 plus 2. And of course, this one is 3. 1 before it was 1. So those are our triangular numbers again. Well, just written in a different way. So that's sigma notation. We'll use that all the time. If anybody's done calculus, this is the notation you use to do Riemann sums in calculus. There's some kind of cool stuff involving that. In fact, I guess where I'm going to end things today is showing you a couple of formulas for particular sums that we can deal with. We just did that the sum from I equals 0 to n of I can be written, that's what the triangular number was, so that's n times n plus 1 over 2. If you want to make something more complicated, try putting other numbers in there, or other functions in there instead of just the identity function. So what do you get if you, for instance, try the sum from I equals 0 to n of I squared? That's an interesting question. Maybe we should play with it a little bit. Let me come back to Sage and we'll play. So I can set this up so we add up the things in a formula, except what I want to be adding on is I squared now. And so I don't want to just go all the time up to 10, so let's go 0 to 0 first. That's not going to be very interesting, is it? If I sum all the squares from 0 and only 0, I get 0. That was silly. How about if we sum the squares of 0 and 1? That's what this loop would do. First we print it. Oh, we kind of really don't want to print x until we're done, do we? Oh well. I wonder if I can do this smart. Outside the loop, we'll print final, and then say x. Is that going to do it? Yeah. All right, so if we're adding up 0, 1, and 2, oh yeah, so that's interesting. We're adding 0, then 1, and then 4, so we get a 5, and the final result there was a 5. 0, 1, 4, and 9. What's that going to be? 14. Okay, so I'm going to stop showing the intermediate results. Let's just comment this out. And in this case, we don't really then need to say the word final there. Print x. Cool. Okay, so I got 14. Now, let's be programmers here. I want to do this over and over again, so I'm going to nest the loop. All right? We're gonna have a loop for say j, and might as well use the real notation that Python programmers would use. If you want to do something over a range that would be the appropriate range for indices into a list, you use the range keyword. So this will get me all the appropriate indices for a list of length 10. That means it goes 0, 1, 2, 3, up to 9. Right? And then I'm going to use j, which I just created in the outer loop, as the index variable, or as the upper limit of the index variable in the inner loop. Now I got to tab everybody in so that the nesting actually happens. I think we can just delete that. And if I run this ought to first print out 0, then 1, then 5, then all the values we just talked about. And I got an error. What did I do wrong? Oh, I forgot to put a colon at the end of the line. Yeah. What? Oh, yeah. So I do want this print statement to be happening inside the outer loop, but outside the inner loop. There we go. So this is the sums of squares. 0, then 1, then 5, then 14, then 30. See how you're getting 16 more on there? And this is a difficult sequence to write a formula for. But I want to show you a little analysis technique that you could use on a thing like this. Suppose you were handed this sequence of numbers and you're like, what the heck is that? You can actually discover that that's the sum of the squares. So let's, on a sheet of paper here, copy down the values. Let's see, will I be able to see the CoCalc screen? Yeah. So write them down in a row. 0, then 1, then 5, then 14, then 30, and then 55. Okay, and we've run out of space on the page, but that'll be enough. A really nice way to analyze a sequence is to look at how the terms differ. From 0 to 1, there's a difference of 1. Right under it, a new sequence that's the difference between things. 0 and 1 gets me a 1. 1 and, I said the answer. 1 and 5 differ by 4. 5 and 14, those differ by 9. Now if you notice that the pattern in the next line is valid, you go, okay, these guys are the differences of something I know. These are the differences rather are something I know. The differences are squares. That must mean these guys are the sums of the squares. So that 30, for instance, has in it 0 plus 1 plus 4 plus 9 plus 16. That's how you get 30. So this is called making a difference table for the thing. And you can do a lot of good analysis with a difference table. Again, for folks who've done calculus or are currently doing calculus, this is very much like the process of taking the derivative. So, just for everybody, you can understand this. The derivative is generically sort of the idea of figuring out how a thing changes. So, by looking at those differences there, I'm thinking about how that thing changes. And something the folks who have done calculus will recognize is that you can do it again, right? If you take one derivative, it's okay to take a derivative of that. So it's kind of instructive to do that. What do you get if you look at the differences between the squares? 3 is the difference between 4 and 1. 9 and 4 differ by 5. 9 and 16 by 7. 16 and 25, those are 9 apart. And in fact, those are just odd numbers. Weirdly, they start at 3, but this whole thing could have been backed up 1. And then we would have had a 0 there, and then we would have had a 0 there. Right? So really the sequence of some of those squares starts with 2 zeros and then heads off. Yeah, keep going, right? Do it a third time. The difference between 1 and 3 is 2. And between 3 and 5, it's 2. And between 5 and 7, okay, it's always 2. So you can think about kind of reversing the process. That is, I've worked this difference table down to the point where I got a fixed number at the bottom. Well, that means I kind of believe this number keeps being 2's, don't I? In that case, 9 and 2, that must be 11 right there. And then this number above the 11 has to be a 36. And what would the number be that I'm not quite got enough space to write? Well, it'd be 55 and 36. That's, well, I can cheat. That's 91. There it is in the Sage worksheet. So this is kind of getting us in the direction of using a difference table to analyze a sequence. What you know when you take in calculus, the folks in calculus will know this, if you take 1, 2, 3 derivatives and you end up with a constant, you must have been looking at something that was a cubic polynomial. If you take 3 derivatives, it goes, first it becomes quadratic, then linear, then a constant. And if you didn't know that, well, just take my word for it. This works. The formula for this sequence we're after has to involve x cubed. So you could start sort of guessing and checking. It's some polynomial in x cubed. But I'd like to be a little more systematic than just guess and check. So I'm going to show you yet another way to analyze a sequence. The sequence we've been talking about is this unknown thing, right? Starting with 0, then 1, 5, 14, 30. Well, that's probably enough of it. And I think that it's a cubic. And I'll just note that the formula we had before for the triangular numbers was a quadratic. Maybe the cubic is related to the quadratic. So what were the triangular numbers? Tn was 0, then 1, 3, 6, 10. And so the other way of analyzing a sequence that I'm interested in, or that I'm trying to illustrate, is to figure out the quotient of these two things. Notice the unknown guy is larger, but, well, a 0 over 0, I don't know what to do with that. So, no. 1 over 1 is 1, 5/3. Then 14 over 6, if I simplify that, that's 7/3. Yeah? And then 30 over 10, well, that's 3. Or 3 over 1. Wait, what if I wrote it over 3, like these last two guys? It'd be 9/3. What's the next term in the sequence? Excuse me. It's 55, right? And the next term in the triangular numbers was 15. What's 55 over 15? There's a common factor of 5, so it's 11/3. Starting to see a pattern? Yeah, it looks like it. So the fact that we're getting a recognizable quotient is helpful. Now, it might help for us to realize what those numbers are. 1. Wait, I was supposed to write it like things over 3. So actually change that one into 3/3. I guess I could leave this one as 1/3, but because it would be 1/3 times 0 gives me. All right. So yeah, what is a formula for these numbers we're getting out? 1, 3, 5, 7, 9, etc. Well, that's obvious, isn't it? They're the odd numbers. So this lets me take a stab at a formula for the unknown sequence. It looks like it's, my friend, the triangular numbers times an odd number over 3. And it's correct. It's normally written slightly differently. We combine the fractions, and you get n times n plus 1 times 2n plus 1 over 6. So let me give you that formula here. n plus 1, 2n plus 1 divided by 6. Let's just finish this off by getting one more of these type of formulas. What do we get if we add up the cubes of our index, running from 0 to some number n? Well, this is so cool because it just it turns out that it's going to be a biquadratic or a 4th degree polynomial. And it's related to one of the earlier ones. In this case, the relationship is so nice. You take the formula for the triangular numbers, and you just square it. So that's really easy. The sum of cubes is the triangular numbers squared. So I almost accidentally signed off without doing an important last couple of things in this section. So let's get started with that. One of them is Just like we can sort of emulate the way a loop can add on things as we pass through it to initialize some variable and then keep adding to it. You can do a similar thing with multiplication. So let me just sort of copy some of this code from the previous example. I'll have to fiddle with the syntax of it, but it'll help. Okay, so I'm going to run through a loop a bunch of times, and then rather than adding something to my variable, I'm going to multiply. Now, you could use this sort of old style notation that x is equal to x times something. What I want to do in this particular one is the index divided by the number 1 bigger than that. But that is a little bit old-fashioned. There's another way to indicate that, which is the times equals. So you write start equals, and then this is saying whatever's in x, multiply by that, and you'll get and you keep multiplying by I over I plus 1 as I ranges from 0 to j. Now there's a couple of things wrong with this. The main thing is that my x has previously been used, so x needs to be reinitialized. Let me set it equal to 0, and then we'll see what happens when I print this x. Uh-oh. Oh yeah, I copied code and then I didn't change the part that mattered. I was going 0 to j. I need to go 0 to something that's defined here, so how about 0 to 6? And the answer came back 0. And maybe in retrospect, that's not surprising, because what did I do? I set the thing to 0 to begin with, and then I multiplied by a bunch of stuff. But you're never going to change 0 by multiplying by things. So this was a dumb way to initialize the variable. It would have been smarter to initialize that variable to 1. If you're going to multiply by something, and when you go through the first loop, the product will be equal to the element in the first, the thing that you multiply by the first time through the loop. If you initialize with 1, that is, it'll happen that way. You initialize with 0, and it's just always going to be 0. And it's still 0. What did I do wrong there? Well, look at what the first entry is in the loop. I think there's too many parentheses in that expression, by the way. But the first entry is when I is 0, you'll get 0 over 1. But that's still 0, so yeah, you're going to kill it. So I really want this to go from 1 to 6, not from 0 to 6. And maybe we'll get something that's not stupid this time. Great. 1/7. 1/7? Really? I mean, I'm multiplying a whole bunch of things together and it just all becomes 1/7? Well, that's an example of something that is in our book here. Well, actually, there's two things in our book that I want you to take a look at. The first is this stuff in the box. I'm on page 264 right now, so if you want to go to 264, you can see the same box. This is the mathematical notation for the same thing I just did in code. Run through a loop and multiply a bunch of things together. So that oddball symbol right there, the boldface, I don't know, it looks like a giant Roman numeral 2, but it's not. It's got a cap along the top and it's open at the bottom. That's the capital letter for pi. And pi is P in Greek. Actually, I've got a friend who's from Greece, and she told me that in Greece, that letter is literally pronounced P, which is funny. Anyway, pi means product, so to write product from k equals 1 to k equals 5 of ak means multiply a1 times a2 times a3 times a4 times a5. Well, they've got the general setup here in the box. You're multiplying a sub k, where k is running from, where is it, m to n. But that'll be the product of all those a sub whatevers from the mth one all the way up to the nth one. Okay. The thing that just happened in my example that I did in Sage was the sort of thing that's seen right above that. Let me scoot this book down a little bit. And this is a common trick. It's a common thing to look for sums, and it can be products that people call them telescoping. Can't get this thing to stay put. The idea of a telescoping sum is it's a little bit like those things you see in old pirate movies, where the telescope that you extend out and then it can be collapsed. All right, I'm stuck with what I'm stuck with, I think. So I'll hold on to it. Okay. Why can't I make this? I'm turning the thing. The problem is it's turned 90 degrees to the way it's being displayed, so it's really hard to manipulate and get the thing to look right on the screen. Anyway, the sum here is actually the sum of 1 over k times k plus 1. That's what they're really interested in. But they've done a little algebra up ahead of time, and you see that the summand, the thing that's being summed, can be re-expressed as a difference of things. And in fact, it's particularly nice. It's 1 over k minus 1 over k plus 1. So here you can see what happens when you have a sum like that. The expanded form is probably the clearest thing, right? If you expand it out so that there's your first term, which consists of these two fractions, there's your second one, which consists of the next two fractions, and so on. There's this cancellation. They've indicated it already in the book. There's a minus a half here, and there's a plus a half here. So those guys knock each other out. And that happens right on down the line. So what we end up with is the first term minus the very last term, or the first part of the first term minus the second part of the very last term. So that's much simpler, and that's an example of telescoping. Now the thing that I just did in Sage on the worksheet there was similar telescoping, but with multiplicative notation. Give me a sec. I gotta change this orientation because it'll make me crazy otherwise. Okay. All right. So what I had was a product of 1 over 2, and then 2 over 3, and then 3 over 4, and so on. It went all the way up to, I believe it was 6 over 7. That is, as we multiplied by different things, the first time through the loop we multiplied 1 by a half. Actually, I guess I could say it was 1 times a half, and then all the rest of those terms. The second time we multiplied by 2/3, and so on. But you see how the telescoping is going to work? There's a 6 in the denominator, there's a 6 in the numerator. Similarly with 5s and 4s and 3s and 2s. The only thing that survives all the cancellation that happens is the 1 in the numerator there, and the 7 in the denominator there. So you get 1 over 7. Okay. So 2 examples of telescoping for you, one in a product and one in a sum. Okay, so there's a chart again in the textbook on page 265, just the very next page from what I was looking at. Gonna have to change orientations again. Excuse me. Oh, gotta kill that. It's so weird to move something and see it move 90 degrees to the way you're pushing it. Anyway, there's a nice property here on page 265, a set of properties that we should take a look at. Just observe that this way of combining a pair of sums, where they're saying a sigma with AKs in it and a sigma with BKs in it, can be turned into a single sum, a single sigma with an AK plus a BK in it. It has a little prerequisite on it. Notice how this first sum goes from k equals m to n, and the second one goes from m to n. They're both the same. They have to be the same sizes, or you can't do this. Right? So that's Well, I suppose that's a pretty reasonable seeming thing. This next line, number 2, is also pretty reasonable. This is just the distribution law, but it's distribution over a large sum, not just C times a couple of things added together, but in this case it would be n minus m, or maybe one more than that, things added together. So, but still, you can distribute multiplication over sums, and so you can, basically it looks like you can just move that constant C inside the sum. There's a similar rule to number 1, just written out for the way products work. As long as the products are the same range, the index goes from m to n in both of these, you can just kind of think about rearranging the bits and reparenthesizing everything and turning it into a single product with the things that match index, with A with the same index times B with the same index can be kind of grouped together. All right, a real important example of the product notation stuff is the a notation called a factorial. So I'm going to run an example of that. Actually, don't need that window anymore. So let's do just exactly what I did here in this cell once again. So I'll copy it over. But I want to change what I multiply by and just have it multiply by I. So this is going to, at I equals, when I is running from 1 to 6, that's going to give me a result where, well, it'll be 1 times 1, then times 2, then times 3, then times 4. It's the product of all the numbers from 1 up to 6, which is 720. We should... I should point out that you've probably seen these numbers before, but let's get a few of them instead of this. So once again, I'll use a loop to kind of encapsulate that loop. We'll nest things. So for j in, how about 1 dot dot 10? Do I dare go that far? They get pretty big fast. That one is going to go from 1 to j now. I will keep reinitializing the variable each time I'm in that outer, or pass into that outer loop, and I do want to print these things within the outside loop, but not within the inside loop. Got it? What's that going to do? It's going to give me an error, of course, because what did I do wrong? What did I do wrong? It says... Oh, I forgot the colon. There we go. Fussy little programming language. Okay, there. So that's an interesting sequence. 1, 2, 6, 24, 120, 720. These are getting large fast. I like that last one because it's just the previous one times 10. You just added an extra 0 to it. That sequence of numbers is called n factorial. You say n factorial, but you actually write n with an exclamation point. I suspect people have seen that before. So yeah, 1 factorial is 1. That makes sense. It's a product with a single thing in it, so you're not really multiplying anything yet. But if you think about it the way our loops worked, we started with the initialized variable. X was 1. Even if we didn't have anything happening inside the loop, that is, if we ended up not multiplying by anything at all, we'd still get 1, which tells you an interesting factoid. I got to display my writing. Oh my! I think I just did that. No, it's just that one thing. Okay. Huh. That one. So we write n factorial. Let me go back over the stuff that I just wrote down while it was hidden. N factorial, n with an exclamation point is how that's written, but you say it as the word factorial. 1 factorial is 1. Here's what my question was. What should we do with 0 factorial? So a lot of people think this is the this is the product of all the numbers starting at n and going down to 1. So we would start with 0, and it wouldn't matter where we'd get 0. But that's not quite what to do. You sort of start with that initialized value we did for the variable. Start with x equal 1, and then don't multiply by anything. That is, have an empty product. It's still going to give you 1. You can think of this as being a definition that we just define that, or it's conventional, but there's very good reason to think that 0 factorial ought to be equal to 1. 0 factorial is an empty product. I gotta mention while we're on it that there's also the notion of an empty sum. What should you do with a sum that doesn't have any terms in it? Well, empty sums are equal to 0. And empty products equal 1. And that, I think from a computer science perspective, you think about how do you initialize the variable before you enter into any loops that are creating either a product or a sum. If you're going to be adding on stuff, you start with 0. If you're going to be multiplying on stuff, you start with 1. Okay, so we've talked about n factorial. While we're talking about n factorial, it's convenient now to mention a related notation called the binomial coefficients. Actually, the way people normally pronounce this is choose. Choice counters. Sometimes you'll see them written like this, C of n and k. But the more standard notation in the math world, you'll see that notation in the Texas Instrument calculators, but in the math world we write n over k in a pair of parentheses, and it looks like you just forgot the fraction bar. Why is my autofocus not working right? There it goes. Yeah, so it looks like the fraction bar is omitted, but it's really supposed to be omitted. So you can tell this means something different than dividing n by k. In fact, what this means is the factorial of n in the numerator of a fraction, the factorial of k in the denominator, and also you figure out their difference, how much they differ by, and put that thing's factorial in the bottom. Let me run an example of that so you'll see it. If I was to calculate 5, choose 3, and that's how you say that, by the way. Let me write it down. 5, choose 3. You would say, okay, it's going to be 5 factorial over 3 factorial. And also 5 minus 3 is 2, so we'll have a 2 factorial down here. The factorials, as we saw in the SAGE worksheet, they grow pretty rapidly, right? I mean, it wasn't long before we got numbers that were pretty big. 5 factorial is actually 120. 3 factorial, well, that's not too crazy. That's 6, and 2 factorial is just 2 from my SAGE worksheet. But this would be, well, this wouldn't be so bad because you get 120 and then there's 12 in the bottom. You can see that this is equal to 10. But I kind of want to show you how the expanded form of that factorial stuff. So let's not jump to the conclusion here. Just pretend these didn't happen. We'll write out the expanded form of the factorial. It's 5 times 4 times 3 times 2 times 1. The other factorial in the bottom has 3 times 2 times 1 and 2 times 1. So, well, how about 3, 2, 1 and 3, 2, 1? Those guys can be canceled, and there's a 2 there that takes care of one of those 2's. That's the way you normally do the cancellation with factorials, because you can. So you don't figure out what they are in advance and then simplify the fraction. You know that this 5 factorial contains all the things of a smaller factorial in it, so you'll be able to just knock them off. In the end, we still got 10. Now that 10 is a number we've seen before. Somewhere along the way, I produced Pascal's triangle for us. And that's the 10 we're talking about. Did I say 5, choose 2? I lied. I said 5, choose 3. That's the 10 we're talking about. That number right there is 5, choose 3. And in Pascal's triangle, the 5 is your row index, and the 3 is your column index. Okay, so there's a couple of issues that I have to say to explain that meaning. One is that the columns are slanty. These are the columns right there. That's not so bad. The rows are straight across. So there's 0th row, 1st row, 2nd row. 3rd. But did you hear me say the 0th row? The indexing works so that that's the k equals 0 row right there. This is k equals 1. The one that I was looking at down here with 5, that's the k equals 5. 0, 1, 2, 3, 4, 5. And the column is the 0th, 1st, 2nd, 3rd column. So that 10 is in the 5, 3 position in this slightly skewed table. Okay? All right, so I guess I'll end the lecture here. There's just a puzzle for you. Gamblers are often really interested in this this binomial coefficient, this choose number, 52 choose 5. Why? Because these things actually tell us how many sets of size k can you pick out of a set of size n, and 52 choose 5, that's the number of ways you can get a 5-card hand out of a deck of 52. So my question to you is, figure out what that number is, because if you want to work out the probabilities, the odds of getting various poker hands, that's going to be the denominator you use for almost everything. Right? Well, for everything. Anyway, that's it for today. This video will be posted. Now it's about 9 o'clock in the evening, so it's going to be a little bit late again. I apologize for that. But hopefully everybody will get a chance to look at it before class tomorrow. I'll see you then.